Hello, my name is Andrea, and today I'll be presenting my project, which has the aim of reducing surgical infection rates by improving water distillation in the Dominican Republic. I would first like to explain the current situation in Dominican Republic in order to highlight the existing problems regarding water distillation. According to the Pan American Health Organization, nearly 7 in 10 hospitals in Latin America and the Caribbean are in disaster-prone areas. Moreover, in 2000, only 48.3% of the population had water supply service. Despite the country's economic improvement during the 1990s, the water quality still remains poor. Medical institutions must meet the optimal water requirements, but the water supply is at risk in some areas, mostly rural ones. The most frequent natural disasters that occur in the Dominican Republic are hurricanes and tropical storms. These affect sewage systems and damage pipelines, which contaminates water with different bacteria. In addition to this, Dominican Republic also shares water resources with Haiti, which is the poorest country in the Americas and the only country with insufficient water resources in the region, according to a report published by the Ministry of Foreign Affairs. Therefore, medical facilities in poorer regions, like the border with Haiti, have less water coverage and lower water standards. Although hospitals provide patients with clean water for all needs, medical equipment such as autoclaves requires distilled water in order to function properly. There are industrial water distillers on the market, but purchasing one would not represent a wise choice for a low research setting. The price ranges from 3,000 to 5,000 euros, and these machines are mainly manufactured in the US or Europe, so installing and especially maintaining one would be difficult. The proposed solution would offer a low-cost system made from easily available materials which harvest solar energy to produce distilled water for healthcare facilities. Here is a diagram which explains how it works. The two phases include water production and water testing. Each component will be later detailed. This is a visual simplified representation of each component of the system. Next, I would like to present with the help of this table who are the potential stakeholders for this machine and what features they might be looking for. Now I will start explaining how each component works. The first one is the sugarcane bagasse filter. This will remove heavy metals from water with the help of sugarcane bagasse, which is a biomass of agricultural waste, mainly made from fibers. Historically, sugarcane has been one of the main crops in Dominican Republic, so using this material represents an affordable and handy solution. The filter relies on the bioabsorption property of the bagasse. This way, metal ions found in water bind to the functional groups present in the biosorbent, in this case carbonyl, hydroxyl, and lignin, and after a certain period of time when equilibrium is attained, the filtered water separates from the biosorbent. The filters will be made of soaked, washed, and oven-dried bagasse, which will then be crushed into a fine powder and pressed in order to become compact. The process will be repeated twice as there will be two filters inside the tube and the water collector at the end of it. Next, the water is heated. The main purpose of the solar heater is to increase the temperature of the partly filtered water in order to speed up the process, as water will heat up and evaporate faster in the solar distiller if it is already brought up to a high temperature. The materials for the solar heater are very accessible and the entire system is easy to assemble. The first layer is made of plywood, followed by a thin aluminum sheet which will help boost heat absorption. Next, a copper pipe which has high thermal conductivity will be placed on top of the aluminum sheet and the entire system will be enclosed with a piece of glass. This will create a greenhouse effect inside. The structure will be placed on a metal frame. It will communicate with the water tank with the help of flexible plastic tubes. The explanation behind this is based on the thermosiphon principle, which is a method of passive heat exchange. Hot water is less dense, so it will move up, replacing cold water. The copper pipe will absorb solar energy and will become extremely hot. Cold water will enter the pipe through one end and, after it will gradually heat up, it will be evacuated through the other end into the water tank. This is a loop principle, and after some time all the water from the tank will be heated. This is the solar distiller. By using solar energy, salts and other contaminants are removed from the water, the process working mostly the same as boiling water and condensing it, simply because by elevating the water temperatures, the evaporation process will begin. To keep the equipment easy to build, the main structure will be made of wood, which acts as a great insulator because it has low thermal conductivity. The inclined covering will be made from glass. An additional black coating will cover the base of the structure in order to keep the water's temperature elevated and maximize solar irradiation. One idea would be to use graphene from coconut shells, which are widely available in the Dominican Republic. These can be turned into charcoal through the process of carbonization, serving as the base for obtaining graphene powder. The evaporation process will result in condensed droplets of water, which will accumulate as the final product. A further control step would be installing a mini solar panel no more than 12 volts that could provide electricity for the elements in a circuit to test the final water pH, which should be around 5.7. A simple pH sensor would be attached to an Arduino board, constantly displaying the pH level on an LCD display module. In this representation, I made a circuit diagram. I tried to take advantage of the sunny climate of Dominican Republic and come up with a solution that relies on solar power. By looking at this chart, it can be seen that temperatures are high all across the year. The design of the system suffered a few modifications along the way. My initial idea was to use the reverse osmosis process, but I found out soon that it was not a viable solution for two reasons. One, even if I used only one membrane for the water to pass through, those materials, which were cellulose acetate and polyamide, were hardly available in the Dominican Republic. And two, in order for the design to function, the water needed to be brought to a pressure of at least 60 pounds per square inch, and this could be achieved only by using a water pressurizer, which would have increased the cost. There are still improvements to be made to this design. Because it relies solely on solar power, the water production will not always be constant. However, one alternative that needs to be further explored is converting and then storing electricity from the photovoltaic system, and after that passing it through a conducting material which will heat up the water from the distillation basin. This might replace the need for sun to help water evaporate.